Okay, let's dive right into this. It's pretty wild to think that a tool humans have used for thousands of years could completely stump some of the brightest engineers of the 20th century. But well, that is exactly what happened with the acoustic horn. So today, in this explainer, we're going to unpack a really fascinating 80-year mathematical mystery about how physicists finally figured out how sound actually travels through a curved space.
And hey, don't worry if the physics sounds a bit intimidating at first. We're going to navigate this dense acoustic journey together using a pretty clear roadmap. First up, the history of the acoustic horn. Then, Webster's plane wave theory. Rayleigh's mathematical struggle. And finally, the boundary element method. Starting off with Section 1, the history of the acoustic horn as a millennia-old tool.
So for literally thousands of years, humans have used horns for music, for summoning, and for listening. But horn design was purely trial and error. It wasn't until around the turn of the 20th century, with the invention of audio recording, that the horn's purpose completely shifted. We didn't want the natural, kind of honky resonances of an old megaphone anymore. Engineers suddenly needed precise directivity control and impedance matching for crisp sound reproduction. That need sparked A.G. Webster's formal model back in 1919, which eventually led all the way to John Post and Elmer Hickson's advanced computer modeling in 1994.
Now, you might be wondering, why is modeling a horn so incredibly difficult in the first place? Well, the core physical problem here is that you're dealing with three-dimensional sound waves trapped in a space that is continually curving and flaring outwards. And to understand why getting this math right is a make-or-break situation for a speaker, we really have to look at one absolutely crucial concept.
Acoustic impedance. Simply put, think of this as the resistance to acoustic flow. The horn is basically acting like an acoustic transformer. Just imagine the intense, physical, high pressure pushing against a tiny speaker cone at the narrow throat of the horn. The horn's job is to efficiently transfer that high-pressure energy into the low-pressure open air of a large room. If you don't have a proper impedance match, it is catastrophic. The sound gets severely distorted, the diaphragm displacement goes completely off the charts, and the driver could literally break itself apart from the violent resistance.
And the stakes here are incredibly high. To put that into perspective, even in modern, high-quality, constant directivity horns, impedance mismatches can be as large as 10 to 1. That is a massive inefficiency. It really highlights exactly why solving this math problem, being able to perfectly predict and shape a horn's acoustic impedance, was absolutely critical for the entire audio industry.
Which brings us right to Section 2, Webster's plane wave theory and the plane wave assumption. This was the very first major breakthrough, published by A.G. Webster in 1919. And to make the math actually solvable by hand, Webster kind of had to pretend the real world didn't exist. He assumed sound acted as 1D plane waves. Imagine water flowing smoothly and perfectly flat through a narrow, straight pipe. But reality is 3D spherical waves. When sound actually travels down a flaring horn, the waves curve and expand outward, a lot more like water dumping out of a pipe and splashing into a large bucket.
Because early engineers just didn't have modern tools, Webster assumed those sound waves stayed perfectly flat, which gave us Webster's horn equation. Now, yes, it was a massive mathematical oversimplification. But the craziest part? It actually worked. Miraculously, it performed surprisingly well, at least near the narrow throat of the horn where the flare was gradual and the sound waves hadn't really started to curve much yet.
But of course, as audio tech advanced, engineers needed way more accurate models. Let's jump into Section 3, Rayleigh's mathematical struggle to find 3D solutions. Okay, don't panic, we are absolutely not doing complex calculus together right now, but it is important to appreciate what engineers like Lord Rayleigh were up against. As the horn flared out toward the wide mouth, Webster's 1D model completely fell apart. To solve for those curving 3D wavefronts, physicists brought in the heavy mathematical artillery. We're talking Bessel functions, iterative methods of successive approximations, and literally swapping standard equations for ordinary differential equations of infinite order. It was months of agonizing manual calculus on chalkboards just trying to map a single sound wave. But then, a massive eureka moment. After all that terrifying math, they uncovered a totally unexpected twist. When they finally crunched the numbers on how the waves curved and transformed, a complex process they call mode conversion, they realized it actually didn't significantly change the acoustic impedance at the throat. Webster's simple, simplified 1D equation from 1919 was remarkably robust for finding throat impedance the whole time. Actually, there's a quote from a researcher named Hall that perfectly sums up the utter frustration of this era. He wrote, The impossibility of verifying more exact theories experimentally has heretofore justified the use of the present horn theory. Basically saying, the real 3D math is just way too hard to prove by hand, so we're just going to give up and keep using the simple, slightly flawed 1919 math. And they did for decades.
Fast forward to the 1990s, and we hit Section 4, the boundary element method and the rise of digital computers. Because let's face it, when human math hits a wall, we bring in the machines. With the falling cost and the absolute explosion in processing speed, physicists could finally ditch the 1D simplifications for good. They could now tackle the actual 3D Helmholtz wave equation directly using powerful numerical methods. So here is how this new computer algorithm, the boundary element method, actually works. First, the computer starts with the Helmholtz integral formula. Second, it applies Green's identity to accurately map the volume of the horn. Third, and this is the absolute genius part, to prevent the math from breaking down into infinity, it isolates the exact point being measured by wrapping it in a microscopic, vanishing sphere. Think of it like a tiny digital bubble that just protects the math from crashing. Finally, it computes the acoustic pressure values strictly along the boundaries, meaning the rigid walls of the horn itself. Okay, so that solves the math inside the rigid walls, but it introduces a classic acoustic headache known as the exterior problem. How do you calculate the sound radiating out of the horn's mouth and into infinite free space? You know, computers, they can't really calculate infinity. Well, the researchers Post and Hickson came up with a brilliantly creative workaround called the fictitious hemisphere. By programming the computer to pretend there is a virtual invisible dome capping the mouth of the horn, they basically exchanged an impossible exterior problem for a perfectly solvable interior one. Problem solved. The computer could finally crunch the exact 3D numbers accurately. And the best part? They didn't just leave it in a computer simulation. They actually had real, physical exponential intractors horns built by hand. They put them in a high-tech hemi-anechoic chamber and tested them using a highly accurate 2-microphone measurement system. And the result was incredible. The modern boundary element method predictions matched the physical reality perfectly. The 80-year scientific mystery of exactly how sound propagated through a horn was finally, definitively solved. It really makes you think, doesn't it? Since we finally solved this 80-year acoustic horn puzzle, what other everyday technologies, things sitting right in our living rooms, are hiding impossibly complex physics just waiting to be accurately modeled? It's fascinating to consider. Well, thank you so much for being a focused learner and joining me on this explainer today. See you next time.